Welcome back, everybody. And Maryanthe will give her third and final lecture about learning from complexity.
All right, so thanks everybody for coming back on this beautiful day. So possibly the first day of spring, yes. So welcome back. So today I want to talk about. So I want to do three things. I want to talk about two interactions of these things we've been talking about with questions in computer science, and then I want to step back and draw some preliminary conclusions. And the occasion to talk about these interactions with CS and algorithms is also a nice occasion to talk about work that was done here and benefited very much from this environment. Okay, so let me step back and remind you of something that happened on Monday, very long ago. So, preamble. So, we were talking about how to understand differences in complexity in classes of graphs, in general, first order theories. So we had been measuring elementary classes of graphs. So you have a class of graphs all satisfying the same axioms of first order logic, and in fact, an infinite, right, a class of infinite graphs. And we were asking questions like, take a particular cardinal lambda and look at the graphs from your family and look at all subsets of size lambda. And let's ask the question, what sorts of things can we count over this set? So we had fixed, okay, so in general, you have a theory T, complete theory T, complete set of axioms of first order logic, and some formula phi x y. But in the case of graphs, that was our running example. You can think about gamma, an elementary class of infinite graphs, and R is just the edge relation. And then this
class means the same formula.
Yes, it means exactly. It means we have the set of sentences of first order logic in the language of graphs are the same on any two in the class. And because it's a class of infinite graphs, there will be more than one. If it were finite, there would only be one because we would know the size and know it of isomorphism. Okay, so what kinds of questions were we asking? Well, if we say this in the language of graphs, any other point, or it could also be a point in A, so any point B in the graph labels A, say with a bunch, the points of A are labeled by zeros and ones according to whether or not it's connected. And we were asking how many different kinds of patterns do you get? Right, so we had the possibility, so we asked, as you look over all infinite sizes lambda and all sets A of size lambda in all graphs in your class, one thing that could happen is you always have no more than lambda patterns. So I had called these partitions, you can call them labelings, you can call them phi types if you want to use the model theoretic language. Always have no more than lambda patterns over sets of size lambda. And this is what we call stable. We briefly venture into color. Okay, so stable was when you have few patterns relative to this infinite size. It could be that you have
and we're only looking distance one in the graph, right? We're not.
Yes, we're only looking distance one. Now, in principle, in general, you have a theory and you fix a formula, and for each individual formula, you could ask about stability. So you could also choose your formula to be one talking about distance two, for example. And there was a background theorem we talked about that said you can also count types using all possible formulas, and that count will be big most of the time, if and only if the single formula is big. So, but here we're just focusing on that. Okay, so, but it could happen that for lambda, for some A, we get more. So this was unstable, and the point was that you're either stable or unstable. So this was, so either in every infinite size, you don't have too many patterns, or in every infinite size, there's some set in which you get too many patterns. But we had also talked about VC dimension. So you could ask the question, is it true that for some A of size lambda, you get all patterns? Right, so having strictly more than the size of A many patterns is a priori not the same as getting all possible patterns. And so if the answer is no, then you're still a VC class, a class of bounded Vapnik-Chervenenkes dimension. Yes, you're not. You have infinite VC or infinite or unbounded VC dimension. So remember we had discussed that in the finite, it still makes sense to ask whether you get have a set of size n over which you get 2 to the n many patterns or not. And there was this polynomial exponential dichotomy coming from the Sauer-Shelah-Perles lemma saying that either you have all patterns or you have bounded away from all patterns. But we had also talked about the fact that in the finite, you don't see this difference between stable and unstable, right? So our picture was, again, this is a picture of a graph. This is the picture of the class of all graphs divided into 3 classes. So you have all graphs, the classes of all classes, graphs. You have the class of bounded VC dimension. I could just say finite VC dimension, but I'm saying bounded VC dimension because maybe if you're talking about finite graphs, it makes sense to say that VC dimension is much smaller than one thing. So finite VC dimension, all classes within that. So you can see all patterns within that. You see not all patterns, but you possibly still see more than lambda. And then stable is a strictly smaller class. Now, what's an example of something that falls in between? So recall we had our half graphs. So suppose we have AI, INR, and BJ, J and R. So suppose we have our A's and our B's indexed by the reals, say, and it was a half graph, meaning that there's an edge between AI and BJ, if and only if I is less than J. So things are connected going forward, but not going backward. And we have no opinion about how the A's connect and how the B's connect. So in this example, we are definitely unstable, right? Because we could pick the set indexed by the rationals, which will be a countable set here. And then we get at least all the Dedekind cuts. So we get uncountably many things over it. So we have an instance of instability. But let's see what the VC dimension is. So if I've got 2 points, what kind of patterns can I have over it? I can have an element connected to both. I can have an element connected to this one and not to this one. I could have an element connected to neither. But already on 2 vertices, I don't have an element connected to this one and not to that one, right? So already my VC dimension is 1. I don't shatter a set of size bigger than 1. Any questions about this? Okay. All right. So we had these 3 classes, which will of course play a role in what we're talking about. Okay. So now let's look at the world of statistical learning. So, all right. So this is okay, so this topic is going to have many connections to the IAS, called the differential privacy. We have work of Pinor Nassim and Dork McSherry Nassim Smith, right? So this very idea. Then my personal connection to this was that I was here in 2018 and Avi invited me to give a talk on stable regularity. So, and he told me I should talk to Shai Moran, who is also here. And this was a great suggestion. So this led to a really productive, conversation, a collaboration that continues to this day. And at that time, Noga was teaching a class over in the math department. And so Shai and I would walk back and forth the class and discuss math. and they were thinking about differential privacy, and I was thinking about stability. And so over the course of a long conversation, you start to see that there are all sorts of interesting connections between these things. So let me tell you a little bit about this story. So this is going to be the story of, so this was a conference paper, this was a conference paper, and then there was a journal paper that combined the two conference papers. And then a recent paper of ours will also be relevant. So this is the story I'll tell now. Okay, and let me, so the disclaimer is I'm speaking as a model theorist, and let me try to tell you the stories if we're going on, right? Okay, so, let's start with the question of statistical learning. So let's describe this as we have some set and we have some collection of subsets. So H is a collection of sets of events. And because I'm going to want to put probability measures on everything, we can assume, so let me suppose, so I don't say anything about measurability, that X is going to be countable. And in due course, we'll also want to put probability measures over H, so we might as well say H is countable and we have the discrete sigma algebra and everything, but this is not necessary. This is just a simplification for the talk. Okay, so suppose that we have this collection of subsets, and we want to ask the question, if somebody puts, so we know what X is and we know what H is. And somebody wants to put a measure on the background set X, they don't tell us what it is. And somebody wants to pick one of the sets, they don't tell us what it is. So I'm going to describe a very simplistic model of learning where they're actually picking one of the sets. But now what they're going to do is give us some small random sample, some finite random sample, and they're going to label it for us. They're going to say, the set I'm thinking of contains not this point, 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 not this point. It contains this point and it doesn't contain this point. Based on this information, can we make a pretty good guess as to which of the sets they had in mind? Now, of course, you can certainly imagine if there are lots and lots of sets and they all start to look alike on finite samples, we wouldn't be able to guess perfectly which one they had in mind, but maybe we can make a guess that's pretty close, and pretty close would be judged also according to the measure they had. Maybe the symmetric difference of our guess with the actual set is less than epsilon. So pack learning gives a way of formalizing this. So again, to state this in an extremely simplistic form. So do we have an algorithm? And an algorithm is just going to be a set theoretic map from finite labeled samples to, say, to hypotheses. We don't necessarily have to guess something in the class, but let's say for now we do. So is it true that you give me an epsilon and you give me a delta? So there are two parameters. Delta is going to say, it could be that some possible samples don't give me very much information and I can't do it. So maybe a small fraction of the time I can't do well. And epsilon is going to be how well I do in the cases where I actually make a good guess. So is it true that for every epsilon and delta, there's an m, which depends on epsilon and delta? And, well, is there an algorithm with a property for every epsilon and delta, there's an m depending on epsilon and delta, so that anytime the adversary puts a measure on the background, x, chooses one of the sets to label it with, and gives me an IID sample, labeled sample of length n, then with probability at least 1 minus delta over the choice of sample, I can make a guess, which is epsilon close to the correct guess. So again, I've put in many simplifications here. Maybe the adversary, maybe the adversary is using a distribution over x cross the labeling. Maybe the adversary isn't really giving me a function. Maybe the adversary is picking something far away from my class and I need to do as well as possible. But so I won't say anything about these cases. So it's a question about the family of sets, whether or not I can produce such an algorithm, right? Whether or not I can learn. But you can also see, perhaps because, at least just speaking personally from my point of view, the question of whether or not you can reconstruct something in a family from a small amount of information is a really interesting question that has lots of model theoretic content. But there's a very different aspect that comes into these questions, because you're not looking at a model, you're not looking for a definition, you're not looking for a particular way to reconstruct. You only have sample access to what's going on. So just to say that these questions also changed a lot the way I think about these objects, and probably there's much more to say. So the fundamental theorem. Okay, so this has a long history. I put some of the references over here. So pack learning is from Valiant's Theory of the Learnable. Vapnik and Chervenenkis and Rumer, Ehrenvogt, Keisler, and Wormuth have, okay, so there's a characterization, let's call it the fundamental theorem of statistical learning. A characterization of exactly when such a class is learnable in terms of a combinatorial property of the class, which is the class is learnable if and only if it has finite VC dimension. Or I guess I should say bounded VC dimensions. So, so this is a priori very surprising that a combinatorial property of the class would tell you exactly when algorithms like this exist, but maybe as a very informal comment as to why something like this would be true. So remember up here that your infinite VC dimension, your unbounded VC dimension, is telling you you have arbitrarily large sets in which you see every possible pattern. So at least it could be plausible that if on arbitrarily large sets you saw every possible pattern, if the adversary just focused on one of these sets and maybe gave you a small piece of this, maybe we just focus our measure here and choose the uniform distribution. The adversary shows us a little piece in our sample and tells us what the labeling is. We've learned nothing about what the rest of the labels are going to be, right? Because anything can happen. So at least it should be plausible that this is going to be a very difficult situation in which to learn. So this is the non-learnability side. What about the learnability side? So for this, you need, because of Vapnik and Chervenenkis and all of the theory here, you need to know that when you have finite VC dimension, you can choose large random samples, which are pretty representative. So suppose that you have a single function, a single set here, and you're randomly choosing elements according to some background distribution. You would expect that as your sample gets bigger and bigger and bigger, the fraction of points in your set compared to the actual measure of the set would get closer and closer. But why should that empirical and actual measure get close enough at the same rate for all possible sets simultaneously? So if you have finite VC dimension, something like this will be true. And so this means that you have a way of choosing with reasonably high probability a sample which gives you a representative picture of the sizes of all of these sets, and then you have a good way of trying to learn. Okay, so right, so this is a theorem. This tells you that you have a precise characterization. Well, I haven't written anything quantitative, but it gives you a precise characterization of when learning is possible. But there are still very interesting questions to observe about how the algorithm works. So let's assume that we have the rationals between 0 and 1. So this is our X. And let's suppose our hypothesis class is thresholds over the rational. So if I want to make this countable, so what do I mean by this? So for every rational number Q, you have somebody who's 0 up to that point, and then 1 everywhere after. Okay, so you have all of these cuts over the rationals. Notice that this is maybe not completely unlike a half. Right? So if you consider this collection of thresholds over the rationals, first of all, what's its VC dimension? So we know from our example up here that the VC dimension is 1. So it will certainly fit the criterion of being learnable. And here's an example of an algorithm that will learn pretty well. So somebody gives you a sample of points and somebody labels them. And thinking of a cut, and the cut happens somewhere above all of these points and below all of these points. So what's a good thing I could do? I could look at the place where I have the biggest 0 and the smallest 1, and I could average them. And indeed, my random sample is likely to not have gaps that are too large between consecutive points, and so this would indeed be a good way to learn. Maybe the actual threshold is here, so I'm a little bit off from the actual answer, but this would be well within the learning guarantee if my sample is big enough. But notice that in this example, the actual answer I give really depends on the points that I saw in the sample. So if somebody gave me a slightly different sample, and in my picture, these two collections of dots have exactly the same size. So I would have taken the 0 here, and I would have taken the 1 here, and I would have averaged them. And so instead of getting that in the first sample, I get this in the second sample, which is again a good guess and close enough to be the correct answer, but is a different answer than the answer I gave the first time. So one question you could ask is, this algorithm seems to be pretty sensitive to the sample. So are algorithms necessarily sensitive to the sample? In fact, it's very sensitive to the sample in the sense that I just moved 1 point, or well, in this case, I moved 2 points, but I could just move 1 point and give a different answer. So could you be learnable by an algorithm which is not so sensitive to the sample? So, so there's a definition. Okay, so sensitivity or non-sensitivity sample. So let's remember. Okay, so now I will give the definition from the Smith paper of differential privacy. So let's first remember, okay, we're used to thinking about these things as being very close. So let's remember why they're actually really far, why they're actually really, really different guesses. So imagine that our algorithm, instead of taking in a sample S and giving some hypothesis, outputted a distribution of hypotheses. So we could have a measure of what it means for two distributions to be different. And then we could say, rather than asking, are the actual hypotheses outputted close as hypotheses, we could ask, are the distributions outputted close as distributions? And then, of course, we could still talk about that pack by taking the distribution you output and sampling from it and getting a hypothesis, which is the actual answer. And notice that if you want to do something like that, that already shows you that here, right, these two things that you thought were the same are actually pretty different. Because if you had a distribution that took in a sample and just gave you the distribution whose support is exactly this hypothesis, right, it gives, measure 1 to this hypothesis. And then you have a distribution that just has support exactly that hypothesis. As distributions, they're extremely different, right? So you look with new eyes and you see that these were actually extremely different guesses. So, all right, so in general, you now have algorithms that are probabilistic. So they're going to output the distribution over hypotheses. Right? Maybe there'll be hypotheses in your class, maybe there'll be hypotheses somewhere else. And we need to say what it means for two distributions to be similar. So we had an epsilon and a delta in pack, well, somewhere here. So now we have another epsilon and another delta, which go with differential privacy, which are not the same as our epsilon and delta in pack. So if you've got some P and Q, so two probability measures with the same sigma algebra and on the same set, you could say for any E, let's look at what's the probability of E, and you could look at what's the probability of E over here in Q, and you ask, this is actual E, the constant, E to the epsilon times this plus delta, and also in the other direction. So Q, this is the epsilon. Plus delta. All right, so if this happens for any two measurable sets, then P and Q are epsilon delta equivalent. And then your definition is going to say that you want your algorithm to have the property that if you just change one sample, so 1 point in the sample, so a unit in my sample is a point with a label. So I change one of these, then the two resulting output distributions are the same in this sense, or close in this sense. What can we say about this? So when epsilon is really small, this is like 1 plus epsilon. So imagine you have 1 plus epsilon. Delta, so epsilon is some small constant. Delta is something that needs to decrease quickly with the sample size. So if your sample size n, and okay, I guess for us in this paper, delta of n is something like 1 over n squared. So you want it to still stay negligible as the sample size gets bigger because you don't want it to allow you to, under cover of darkness, reveal things about any particular element of the set. Should I say anything else about this? Okay, so at least this was an example of how this particular class, okay, here's an example of an algorithm which learns this particular class but is not differentially private. That's of course not a proof that there doesn't exist such an algorithm. So in general, could you learn thresholds with a differentially private algorithm which is proper, which is outputting distributions over hypotheses, which are thresholds? So the answer is no, and this is due to Van Nissim, Stemmer, and Vadhan. So it takes a lot more work to show that no such algorithm exists. So what does this have to do with stability? So
in this interval, if you instead of taking the direct delta, the average, you take uniform measure on the length, it does not work.
Okay, so that's a good question. So notice, all right, so maybe this is a good point, a good moment to emphasize, since I didn't write it on the board. The differential privacy guarantee is telling you about every possible, you have two samples of size m, so you have two sequences of pairs that are point comma label. And it's not only telling you about things you might be getting from a probability distribution. It's about any two samples of length n. So let's suppose, for example, my algorithm was always going to, take in the 0 and the 1 where things change and just output the uniform distribution. So there's a case where, let's say I have all the zeros over here, I have all the ones over here, and maybe I could have okay, so this is the biggest 0 and this is the biggest 1. And so let me draw the hypotheses over here. So I'm outputting a distribution of hypotheses. And so this set of hypotheses has measure 1, right? It's in fact the uniform distribution. But if I took, if I changed the label, so this label is now 1, so now all of a sudden my algorithm thinks this is where things are going on. This huge thing that had huge measure before now essentially has measure 0. And maybe there's a little overlap the way I drew it. Right. So this is a problem with differential privacy because you have a huge event, right? A huge subset of your hypotheses, which gets really big measure in one case and really small measure in the other case just by changing one sound. So
it's non-sensitivity or even an output of one thing in the.
It's yes, any one thing. So your algorithm has to be defined in any possible sample. And so your condition is saying that no matter what you give me some set of n tuples from x cross 0, 1. And I take this and I produce some distribution of hypotheses, and you look at the sequence and you change one of them. That could mean you change the value of x, that could mean you change the label, it could mean you change both. And then the output can't really change its mind on any measurable subset of hypotheses. In our case, all subsets, because we're taking the discrete sigma algebra. Yes.
I think I missed something. So can you explain to me what is wrong with this algorithm? So let's say I just count how many zeros I have. Let's say I have n samples. I count how many zeros, and then I assume that if I had m zeros and n samples, then it's going to be around m over n, and I'm going to just output it. So I mean, does it need to work in the average case? Are the inputs average, or the inputs can be worst case?
So it needs to work for every possible input. right? So not just the, well, are you asking, does the learning need to work or does the privacy need to work?
Okay, in the algorithm I suggested, I thought that it would be private because I'm just counting how many zeros I had and I'm kind of guessing just based on this where this cut should be. Like if you gave me a random sequence of zeros and ones, then maybe the number of zeros would just tell me where this cut is.
But for example here, right, you've got 4 zeros, you've got 4 ones, right? So what is your algorithm going to do?
I'm saying I'm only counting the number of zeros, and then I'm guessing where the cut is based on like, so if I got n samples and I had m zeros, then I'll guess m over n.
Oh, but is this not very similar to what we were doing before? Maybe we should.
The point is that each individual is like, each point in the data is like an individual. You ask yourself, should I join the database or shouldn't I? If I join, will something be revealed about me? So if I wasn't in the database and I joined it, now number of ones by one, to make a change and
Yeah, but it's a
so
very
my
small
value will
change.
be revealed. So
But it's a very small change in the case I suggested.
small, not small, it made a change. So, so that's not private.
Oh, okay, I thought that you. Okay, maybe I missed the. I thought you can make a small. You just don't want to make a big change by changing one value. Okay, maybe I'll ask you
So
about
maybe
this.
we'll, okay, thank you. And maybe another question for you is whether are you outputting distributions or you're outputting actual hypotheses? Because it is a learner, right? You know, whatever the sample is, if you're getting similar information, you should output at the very end something that's similar to the answer. But if you consider it as a distribution, it shouldn't be. That's a different question. Okay.
Sorry, maybe can I ask another question? Like what I would want to do is some sort of average procedure where I initially take some algorithm and then I look at all possible perturbations I can do and take an average over all the outputs of my algorithm and then maybe iterate this process. And then your claim, I guess, is that you'll never find some convergent, like this thing will never converge in some sense.
Okay, so first of all, it's okay. To prove that there's no such algorithm as a theorem.
Mhm.
Okay? So I can't say very much about their proof. I can say in general, if you want to prove that it isn't going to be possible even with, okay, so what ended up happening in this paper was that you can't do it even with something which isn't necessarily proper. So you don't necessarily assume that the algorithm is outputting distributions over thresholds, it over cuts. It could be in general. So first of all, you're not saying that it couldn't work in many cases, but you have to work hard to actually find. So you have your algorithm and you assume for a contradiction that would work, and then you use the algorithm to find a place where it has a blind spot. So there's the Ramsey theoretic argument. So you really find a place where the algorithm is outputting something which is homogeneous enough that you can spin your wheels and you can get a contradiction. But this isn't to say that you couldn't hypothetically in some cases get some kind of convergence. But there really is a strong dichotomy between can you always guarantee it and can you not. Okay, so let me quickly say a few things. All right, so maybe we know that the fundamental theorem of statistical learning tells us that you're back learnable if and only if you have an VC dimension. And so the content of, so this is stated in a very different language because there are beautiful analogs of this already within computer science, but I would state it in my language as you're differentially privately pack learnable if and only if you're stable. And I should be careful to say that, so if you get rid of delta, and you have pure differential privacy, and then there were different other characterizations that were known. So when I say differential privacy, I always mean approximate differential privacy. So my delta exists. So let's see a non-example. So suppose you have two cases. I have a case where I have an equivalence relation with finitely many infinite classes. I have a case where I've got my thresholds over the rationals. So what kind of phenomena would we expect would go with something like differentially privately learnable, and what kind of phenomena would we expect go with something like not? So we've already seen, in fact, we already know that just pure thresholds we're going to have some sort of problem because the information you get from a finite sample is never enough to pin down a threshold exactly. Maybe the word convergence is not a bad word. And there will be, of course, lots of points that have no effect in your answer, but there may be points that affect it significantly. If, for example, we had a finite number of, okay, so this is a non-example because it's essentially completely trivial, but nonetheless not totally useless. Suppose we had finitely many disjoint infinite sets, and we start sampling from them, and we're trying to guess which one we're in. So until we see all of them, maybe we don't know. But the moment we see this is the set where we are, and we get a label saying this is where we are, we know exactly, right? So it's possible to know exactly what the answer is. And not only that, as our sample continues, it's likely that we'll get the right answer lots, right? We won't just get 1 point saying that, that this is the right answer. We'll get a very strong signal saying it's the right answer. So in this case, you can imagine how you get something like differential privacy essentially for free, because changing any 1 point, won't change the fact that you got the right answer multiple times. So let's, for fun, look again at the unstable formula theorem. So we have this. So we know that thresholds are at least an example of the kind of non-differential privacy you could get in one case. So the unstable formula theorem tells us something about the kind of phenomena in nature we would expect all happen at the same time as thresholds. So let's see what it says, and let's see what else we might expect that we should be able to look for. So remember, in this case, so we have a theory T, complete theory T, and we have a formula. But you can also think about it as an elementary class of graphs, the graph edge relation. Okay, so one thing was that your lambda unstable, all infinite lambda, and again, this was you look at somebody in the class, you look at a set A, and you ask if there are strictly more than A many patterns or labelings or partitions. To lambda unstable, some lambda, 3 order property, which is what we had been calling a half graph. So is there, an infinite set of A's and an infinite set of B's so that your formula holds going forward and not going back? We had half graphs that were arbitrarily large finite, that were indexed by any infinite linear order, by any linear order at all. We had these stability trees of arbitrarily large finite height, and in fact of arbitrarily large ordinal height. Remember that these stability trees we had talked about were things like you have an A empty set, an A1, an A0. So you have the internal nodes of your binary tree labeled by points in the domain, and you ask that this tree is shattered by your formula in the sense that if you make any branch correspond to a set of instances of phi, going right means you add phi x A empty set, and going left means you add not phi x A1. So every path corresponds to a set of positive and negative instances, or connect and don't connect. And then you ask, is there an element that satisfies all of them for every one of the paths? So you have an arbitrarily large half graphs, and only if you have arbitrarily large stability trees. There's an item that I won't mention very much about, but just certain ranks are infinite. So maybe all I'll say about this is that stability trees naturally look like a kind of dynamic process. And there's also a way in which that makes sense in this context. But the two I want to mention here that we didn't talk about on Monday are, okay, so this is the complicated side. So unstable, large half graphs, large stability trees. Some phi type is not definable. and 7 phi types are not uniformly definable. So maybe this is also interesting from the finitary point of view, even though this is really an infinitary statement. It's asking you whether or not there's a kind of strong sample compression. So you're saying you look at your huge infinite set in your huge model of the theory or of the graph, and you've got a particular pattern corresponding to this formula, and you ask, is there a finite set of parameters and a first order set of instructions that based on that set of parameters tell you how to reconstruct the entire type? And 7 is saying that if you can do that for every individual type, you can actually do it in a uniform way. And so just to step back for a minute, we can maybe see at a very high level how all these things would go together. So we talked last time, or we talked on Monday, about instability goes with half graphs, goes with stability trees. But also, if you want to have few types, so looking at the contrapositive, you want to have few types, that is very naturally connected with every type being controlled by its restriction to a finite set. Because then to count types, you're counting finite subsets, of which there are many fewer than the power set of lambda. Why is it that the moment you get definability, you get uniform definability? Because these stability trees are telling you something about whether or not you can recursively partition your domain, whether or not that continues or whether or not that stops. And the moment you know there's a uniform finite bound in the size of a stability tree like this, you have a built-in notion of dimension. Because for every finite limiting formulas or for every point on this tree, you can assign a number, a dimension, an integer that tells you how much more of a tree do you have in front of you. So there's a notion of small and large that comes associated with the stability trees being bounded. And so what the definition amounts to essentially is saying that, there's a finite version space, there's a finite piece of the type. Based on that, you know exactly what the dimension should be, and then you add other formulas on if they keep the dimension at the right level. So there's a very nice picture of how these things all fit together. So okay, so since I want to say a couple of other things, maybe I'll just wrap up this part of the discussion. So what this is telling us, so this suggests a dichotomy. So for theories, but perhaps also for hypothesis classes. So either you are unstable, you have infinite Middleton dimensions, so you have arbitrarily large half graphs, or you're stable, you have finite Middleton dimension, you're online learnable, and in this case, you have some kind of dimension theory and sometimes definability. And maybe the picture of the finitely many equivalence classes was not completely irrelevant. So the theorem of non-Livni and Chimaron, is that a class is differentially privately, again, approximately differentially privately learnable if and only if it has finite Middleton dimension, which in my language is stable. So the finite Middleton dimension, and in fact, finite Middleton dimension is if and only if online learnable. So the statement of the theorem is you're privately learnable if and only if you're online learnable. And yes, so let me also say very clearly, I'm I'm describing this to point out maybe a conceptual similarity between these two very different areas, which I find very interesting. But there's a huge amount of work left to be done, right? So already, even if you realize that thresholds, the half graphs, are important, they had proved that you have to understand. They had proved that you can't privately learn thresholds with a proper algorithm, and left it as an open question whether you can do it in general. So even if you see half graphs or something you should pay attention to, actually dealing with them requires a lot of thought. And also the question of, in the von Livni-Moran paper, trying to understand exactly how these dimensions are going to help you. They have this beautiful idea of a frequent hypothesis, learning with an algorithm that will, with probability bounded away from zero, depending the answer, what you output will depend on the measure, but it will output something frequently. So there are a lot of interesting questions here. I should say that even if you're thinking about this as a model theorist and trying to look for these definitions here, trying to look for these phenomena here, this forces you to ask quantitative questions that you might not otherwise ask. We know there are definitions, but we don't know how easy it is to find them, right? And how many of them there are, and do we have sample access to them? So it starts to ask very interesting questions, which you don't really see by putting measures on infinite models, except in a very vague way. But you see in a very concrete way when you try to finitize these questions to regions where this has a strong picture. Okay, so this is what I wanted to say about this part. So I want to make one more comment. Well, maybe one more. Very briefly, one other picture of work before I draw some conclusions. Questions about this part of the talk? Okay, so this was another. Okay, so I'll just perhaps say briefly. So I wanted to describe a little bit of a motivation of a project with Leonardo Corigliano. And you could also describe this in very different ways. So Corigliano and Rozborov had thought about generalizations of graphons to hypergraphs and arbitrary finite relational structures. And that's one way to see where this work is coming from. But from my point of view, it's asking the question, how can you pack-learn models? And this also has a strong IIS connection because Corigliano was here for a couple of years during a crucial part of this work. So let me just motivate this question, because the first part of the talk, perhaps, and some of the things last week had to do with thinking about well-defined questions and looking at specific interactions around those questions. This is maybe a more open-ended interaction of model theory and learning theory, but which for me personally has also changed the way I think about these models. And so this was nice, thought it would be nice to a bit motivated with people here. So let's ask the question. So let me give you two examples. So suppose I have a family of graphs. On vertex set X. Okay. And maybe that's 1, and 2 will be, suppose I have the convex sets of the plane. So I want to ask, how can I pack-learn these? And maybe it's an interesting question to ask because you might think there's an obvious answer, right? So again, this is, I've got a set X and I've got a bunch of different graphs on it, right? Different possible graphs in my family. The convex sets in the plane, here they are. All my different convex sets. Now, why is there even a question of can we pack-learn it? Well, I've given you these objects in a way that makes them look higher dimensional, but pack-learning is about a set, the collection of subsets. So what's the problem? So why can't we just present these? Maybe I'll call this vertex set V. Maybe that's better notation. So I have a family of graphs on a vertex set V. I want to make it look like my XH of pack. So I just, so that's easy to do. I just let X be V cross V. And I want to encode the edges of my graph. So for each v cross v, for each element in v cross v, I put a 1 if it's an edge and a 0 if it's not an edge. Okay, so this gives a perfectly good way of encoding a family of graphs as a family of unary structures. Likewise, with the convex sets, I could just take, R cross R, and I could put a 0 on all the pairs of points which are in my set and a 1 otherwise. So what's the problem? I've successfully encoded these higher dimensional objects as something which I can then pack learn. The problem is that the fundamental theorem of pack learning is an if and only if, right? I can only learn if it has finite BC dimension. And in both of these cases, it could happen, well, here's a specific example. The convex sets have infinite BC dimension, right? So take a set of points around the perimeter of a circle and choose any finitely many of them, and their convex hull doesn't contain the others. So yes, I can encode this as a unary set, set, but I can't learn it. I can't learn it not because it's not unary, but because it has dimension which is on the wrong side of the fundamental theorem. Also, if you have a family of graphs on a vertex set, this family could be extremely simple and still have infinite BC dimension. For example, consider my family of graphs to be the family of all matchings. So every point is connected to exactly one other point. So whatever our notion of complexity is for graphs, it shouldn't say that graphs of degree 1 are complicated. But when I try to do this translation, I have a particular point. So this is the point A comma B. This will be labeled 0 if in a particular graph, A and B are matched up, right? And so, whether A1, B1 are matched up and A2, B2 are matched up are completely, if these are disjoint points, they're completely independent questions from each other. So the family of all matchings has infinite BC dimension, even though it's a family of graphs of degree 1. And you can sort of see this if you think about what PAC is doing, because the family of convex sets does have a lot of structure. The family of, matchings does have a lot of structure. But, if you're just picking arbitrary pairs of points, you'll probably never see even that the graph has degree 1. You're not going to repeat endpoints. If you're just picking pairs of points in the plane, how do you see that the convex sets have a lot of structure? Well, one way to have a lot of structure is anytime you look at a vertical or horizontal set, the family of convex sets then becomes a family of intervals. So a VC dimension 1 or 2, right? So along each vertical or horizontal slice, you have a much more well-defined family, much more well-behaved family. But if you're just picking points in the plane, you're unlikely to repeat vertical and horizontal slices. And so you're unlikely to see the structure that could allow you to learn. So what we were trying to do in this case was to ask the question, what if we're dealing with families of structures, which of course we could encode as lower dimensional things, as one always does, but what if they have higher dimensional structure, which could allow you to learn? And you have to remember that they're higher dimensional in order to be able to do that. So for example, with the convex sets in the plane, if your sampling were different, instead of just picking an IID sample of points in the plane, you had a measure on R and a measure on this axis, a measure on this axis. You picked some sample of points here, you picked some sample of points here, you formed the grid, and then your adversary labeled the points of this grid with which ones are in my set. Then it should be plausible that it would be much more possible to learn. But in order to do this, you have to, this is no longer an IID sample. The theory only allows you to really use independent samples. So you have to rebuild the theory in order to be able to do this. Likewise with the graphs, if you had, you had your family of graphs, so here's our vertex set V, maybe a much more natural thing to do would be to take a sample of vertices and receive the entire induced subgraph on that, which is again not IID because you're receiving all this information about all the different edges. So okay, so the work of this paper is to prove a fundamental theorem of learning for this high arity learning. And it comes with the dimensions. In this case, the dimension is the analog. So in 2 dimensions, it's the analog of every possible slice, gives finite BC dimension, and in higher dimensions, you have an inductive version of that. But so you have the dimension, you have a notion of uniform convergence, which looks more like grids. You have various other pieces that go with this. And there's an interesting interplay. So another place, people may describe this differently, but from the model theoretic side, another place that you can imagine model theory coming in is in these two examples, we had two very different kinds of things going on. We had the form a grid, right? Two samples and form the grid, which is looking a little bit like a bipartite graph. We had the choose a collection of points and receive the induced substructure, which is a little bit like, you know, it's a power measure, right? Rather than a product measure. You're choosing an actual substructure of the model. And this is something you don't see in one dimension, but there's a very interesting interaction between properties of dimension, which often come as formulas, as half graphs, as things that are bi-induced, and properties of substructures, which often come as a complete unit. So you have to sort of see the interaction between these things. Okay, so this is a good point to step back for a minute. All right, so I would like to make some general remarks. So all right, so so we have been talking about learning from complexity. Okay, so maybe we can. So there's much more to do, and we're still perhaps preliminary to make really big picture comments. But let me try to say a few things. So at least what do I mean in this sequence of examples by the question of learning from complexity? So we have seen things like, let me get my coffee so I can consult my list. So we've seen like things like looking at too many types, right? So how many different things can you see over a set of a given size? We started with this example, so too many types, too many partitions, too many labelings. We've seen this question of irregular pairs and the regularity lemma, which again, when you look at it, is it a small problem or is it a big problem? Is it a signal of a very different kind of complexity or a small amount of complexity? We've seen questions of sensitivity to the sample. We've seen the question of how do you introduce a notion of higher dimension in order to take advantage of higher dimensional structure that might allow you to learn. In the P&T question, we saw examples of two things that initially seem a little bit similar, but it's hard to know how deep the similarity goes. You want to spread out the sets in any possible way to prevent a pseudo-intersection, or you want to force them to be lined up in the form of a tower to prevent a pseudo-intersection. So the kind of complexity you see in these different cases may be hard to get a handle on because any particular example is not very general. Right? You don't know if what you're seeing is something which is really an important difference, or which is something which is an artifact of the sample you're looking at. So perhaps complexity in these cases is, it's a kind of excess. It's something you're trying to measure, but doesn't necessarily fit the tools you have to measure it. So one theme in the kinds of problems and theorems we've been looking at is there is this, beautiful collection of numbers introduced by set theory, which is not necessarily accessible to a lot of mathematical work because you don't often have things that are the right size to use these numbers. But perhaps model theory has sometimes a way of taking the structures you're looking at and putting them in a frame where they do vary along this axis. With the axis of the infinite cardinals, you can have more perhaps sophisticated measurement. I don't know to say sophisticated, but you can have other more detailed kinds of measurements like ultrafilters on these infinite cardinals. So you have this extra axis that gets introduced into the problem, and you have a way of taking the objects you're thinking about and putting them in a framework where they can actually vary along that axis, and something can be measured in that sense. And when successful, that allows you to see something about a strong difference in behavior. Perhaps in the case of P&T, you look from these very large scales and you start to see that actually these two things really are similar. In other cases, you see just a small difference in the existence of irregular pairs, and you look from a very large scale, and you start to see that these things are actually very different. So the introduction of this other scale can sometimes allow you to see things which after the fact can just be expressed as half graphs or as definitions for types or whatever else you like, but don't necessarily mention this venture through the infinite world, but somehow this was a very useful way to see them. So I told you a little bit about the model theoretic problems in the background of these investigations and saturation of ultrapowers and so on. And okay, so there's much more to say, but we'll stop there.
Thank you. Any questions?
So, yeah, of course, you didn't really show the proof, but I was just wondering when you actually use this theory to prove things, let's say, in learning, are you applying this theorem plus a compactness argument, or is it just some like, it tells you what to look for, but then you give a completely combinatorial?
Are you saying you're talking about the differential privacy?
For example,
Yes,
yeah.
For example. So it's absolutely not that you can, well, so there's a lot of hard learning work that has to happen. I mean, so there are parts of this that you can quote. So for example, one thing that I think the most efficient part of the argument already exists in the model theoretic literature is this question of you have half graphs in your stability trees. So we had said at some point, Shelah tells you they're both finite together, or they're both infinite together, and Hodges had proved that if you have, that there's a log dependence in both directions. So this was a paper from the 80s from 1980, perhaps, of Hodges and model theory, and that bound actually plays a role in proof. But for everything else, the worlds are really quite different, and you know, just because, so even if you were trying to produce an argument in which you quoted different aspects of this, you would have to do a lot of difficult work, because there's nothing, not only is there not anything effective about this, but it's not even things that are happening on scales that you can necessarily see, right? For example, let's say you know that a definition exists. Maybe if all you're getting is samples, maybe you wouldn't even have positive probability of seeing a definition. That's not true. I mean, it's actually the case that you know, you can show with probability 1 that you can see something which is a definition which is correct up to measure 0. This was later work with Shelah. But this is very much not obvious in advance. So the kinds of things that go into this argument involve very much work on the side of learning theory. So for the side of trying to prove that in general you can't learn thresholds even with, okay, so if you know your class is unstable, then you have a set where you have these arbitrarily large half graphs, and you know that you could have lots of other hypotheses there. You don't have the pure hypotheses, or you don't have the pure half graphs. So you know you're going to have to deal with these other hypotheses, but how do you deal with them? You know, how do you show that that's actually going to be a problem for an algorithm? How do you actually get a failure of differential privacy? This really requires thinking about what the algorithm is doing. And in the other direction, in the direction where you're trying to show that you are differentially privately invertible. Okay, so again, the way they did this was by showing you have some kind of a frequent hypothesis. You know, you might say from the model theoretic point of view that it's very natural that you have, you know, you have a notion of dimension, you have a hypothesis of maximal dimension. The moment you know exactly how many errors you've made the moment you have a definition for your hypothesis, you know exactly who it is. But your pet guarantee is not allowing you an infinite amount of time or even an arbitrarily large amount of time in order to get an answer. You have an answer based on samples of size n, and it has to be pretty good. So that also requires a lot of rethinking of what goes on. So just on a personal note, it was just a it really causes you to ask lots of very interesting questions about these objects from model theory you thought you knew well, right? These are questions that are meaningful and interact in an interesting way with these model theoretic objects, but show a lot you don't know about them. And so it was, yeah, it's a really beautiful world. And oh, maybe I should also say, so this paper, so with Shelah, so after this paper, after these sort of things, we asked the question, if you look at the unstable formula theorem, it tells you that you would expect all of these phenomena to go together in the infinite world. And in the finite world, some of them go together and some of them don't. So if you really believe this is kind of a law of nature, that all of these things happen at the same time, you should ask the question, if we look in the finite world, do we see analogs of all of them, possibly in different names? So we wrote this paper called The Unstable Formula Theorem Revisited via Algorithms, where we tried to look and understand. So some things we had to prove, some things were in the literature under different names, right? Do all of these things really exist? So that was a very fun paper to write. I mean, so that somehow the independent development is very interesting. But it's definitely not just a quotation. More comments, questions?
Maybe one more question. So you've been taking the point of view that differential privacy is about not the data not leaking into the algorithm in some sense. But I guess there's an alternate framing on it, which is that it's continuous in the data set. Like the algorithm is continuous in the data set, that if you perturb things slowly, if you perturb the data set by a little bit, then the algorithm doesn't change too much. Is that a productive viewpoint for some of this work? Because in practice, when you're learning algorithms, let's say machine learning, you're learning them in some sort of continuous fashion.
Mm-hmm.
And I wonder what your view, how you think about that.
So that's an interesting question. I would. I think there's probably something to say, but maybe I don't want to formulate it. Yeah. No, there's yeah. Any interesting things to say? So maybe we can talk later.
Okay, let us thank Maryanthe both for this lecture and for all three of her lectures.